So good morning, everybody. My name is Martin Wakeman. I'm visiting scientist at EPFL, working in Veronique's lab, and together with some past work by Stephen Hancock, this morning we're going to give you an overview of cost modeling as a tool for sustainable innovation. The objectives of the lecture are to give you an appreciation, your technical people, how to use costing tools to paint a picture of an innovation. So how could you assess a novel technology financially? There are other lectures in the series that go beyond costs to look at NPV and return on investment. But in order to look at return on investment and NPV, you need to understand the basic cost. So today we're talking about costs. So to help you build, and my laser pointer is a class 1 laser pointer which barely works, but here we are. To help you build solid and useful models to aid in assessing innovation and different strategies to scale up your innovation. And it's to give you some language and tools, some of which you may be familiar with, but to speak with other people in organizations. You may wonder why this picture is on here. Very old book, which I really like, about manipulating opinion with data. And cost modeling generates numbers, it generates positions. And when you look at cost models, you need to be critical of the data that's gone into them and how they've been constructed, okay? Because there can be a bias behind the person making the cost model because they want to prove a point. Before we start, a bit of background about myself so you know who's speaking to you. I started off in aerospace with British Aerospace, then did a degree in mechanical engineering, so I'm a mechanical engineer, PhD in composites, which was all very technical. Then came to EPFL for 10 years working as a postdoc, and at that time we were trying to implement a new technology we developed in the lab, so we needed to convince industry to give us money. So for this, we started to develop cost modeling to try and show the business case for composites. So why should Mercedes put their hand in their pocket and give us cash to do the research? You need to look at the business case and the motivation for the work. I spent 10 years at EPFL, and we actually ended up doing cost modeling consultancy for large companies, Ford, Volvo, Scania Trucks, these kinds of people. After this, I went to DuPont as a composites expert, carrying on in composites research, but more and more getting involved with customers, value proposition, doing some cost modeling, looking at the scale up of our process and the economics of that, carrying on doing the technical work. And then the last 2 years, I was involved in a merger and acquisition team, looking at billion-dollar level investments in the advanced material space and where composites could fit into that. So after that, I'm now back at EPFL as a visiting scientist, and my interests are 3D printing, composites, and more recently, sustainability and the circular economy with respect to composites. So the motivation behind the work in our lab was to try and make vehicles more efficient, try and reduce their weight. CO2 is going up, we all know this, and vehicles have made enormous progress in reducing their emissions. However, we're using them more and more, and with vehicles representing a large proportion of emissions in Europe, they are an important topic to look at. So our motivation was to try and reduce vehicle weight because weight correlates with CO2 emissions. And if we can make the vehicle lighter, we can emit less CO2. But we need to do this in a cost-effective way. And often it's using more costly materials like carbon fiber, costs more than steel. So how can we justify that? You can see that weight has remained relatively static over the last 15 years. And we need to start to bring this down also in electric vehicles. So that's a quick introduction. Today we're going to look at cost modeling approaches. We're going to take a deep dive into technical cost modeling. We'll look briefly at cost modeling and technical strategy, just a short look. And then we're going to link cost modeling and sustainability together with a coupled cost model, life cycle analysis, and life cycle costing case study. And then at the end, we're going to have on Doodle a simple cost tool, which you can use in your projects. Also to understand what we're talking about, you can play around with numbers in and see what the graphs do yourself. So imagine you're in this plant. Now, this should now work, and there may even be some sound if it works, but you never know. Not, seems not. Don't know why. Anyway, this is a video taken inside a steel stamping plant. So if you were wanting to introduce a composite component and you wanted to say we have a value proposition against metal, you need to understand both the cost of the composite parts and the metallic incumbent. So how can you model these kinds of processes? What kind of tools can you use? Because here you're accumulating, you're buying materials, you have CapEx, you have robots, specific fixtures that are dependent only on the parts. How can you understand this picture? Okay, so you have to think of your idea. How can I scale it up? Try and imagine it. So just to give you a taste of, what a manufacturing line can look at. And I actually went to see one of these lines in the US on one occasion. And for our composite engineers, this is something we need to sit and stare at and contemplate our own technology against. How can we get into such an entrenched business with all this entrenched capital and engineering? It's a big challenge. So that's the same with introducing any kind of new technology. You have to look at what you're competing against. So cost modeling can help a startup company to assess the viability of your idea and look at how to scale up with time, because how you make a product at low volume isn't how you'll make it at high volume, and you'll need different CapEx. You may even use different materials, different locations, different supply chain. And you can model this, and you can model the different stages. You could be an engineer or an industry where you're trying to screen different materials and processes from different suppliers, and you need a way to understand how they compare from a cost perspective. It could be a bigger industry initiative where you want to quantify a value proposition and work out your business financials. And I've used cost modeling in all these different stages and also in R&D strategy, trying to look at different investment candidates and doing 10, 50, 90 models, looking at what can technology do to change the cost, to change the market penetration, to change the business case. So you need to understand the basic cost position of your idea or your product. So here, this is a car seat. This is a Volvo ET car seat made in steel. And in our lab, we had a project. You can look at this part later. Try and make this in composite. And it was funded by a big industrial consortium. And we did a lot of cost modeling in the project to try and convince stakeholders in the company. For example, the molding tool to make this costs 300,000 euros. So somebody has to convince their manager, dip their hand in their pockets to make a tool for a prototype. And that's a big ask. Okay? That kind of money elevates in the organization. You need higher level approvals. So you need to start to answer questions. So if you click on this image, you can start to type in what you think needs to go into a cost model. If you point your mobile phone at this barcode, it should work. I tested it yesterday. And then you can type in some things that you think need to go into a cost model. I hope it works. Try it myself as well.
And you can say what you think should go into the cost model.
Yeah. So the question seems to have disappeared.
Huh.
I thought there might be a problem with the first one, because once you've used it once, you can't reuse it.
Oh.
So the second one later on will work, because I didn't test that. So I'm trying to type in the question now. We're going to have to probably skip this one. So what should go into a cost model? And this is supposed to work, but you can then
then you should say something.
But anyway, the second one later on will work, because I haven't played with it since I created it. But
we have one question here.
Go on, sorry.
I'm sorry, what is a composite?
Composite is a mix of a fibrous material and a resin. So you could take mud and straw as a simple example. You could take epoxy resin and carbon fiber as another example. does anybody in here have anything made of carbon fiber?
Your bike?
What do you have?
I was working on some exoskeleton.
Okay.
Carbon fiber for some of the parts.
Okay. So you might have skis that have carbon fiber in. You may have a bike that has carbon fiber in. Many different things have carbon fiber in. So if you're looking at mountain bikes, the most expensive ones are in carbon fiber because they're lighter. Maybe they're more fragile, maybe not. Okay, so that's what carbon fiber is. So these are some of the elements that go into a cost model. You need your materials, your bill of materials, and you may have multiple materials. Here, it's just 2 materials. If you're trying to make a sensing object, you may have 50 materials that go into there. You may use many different suppliers, but you need to include all your materials. And in your process, there will be some trim and some rejects. And we're going to talk about that. So if you're making a jacket, the tailor will take a roll of fabric and he'll cut some out to make the shape. Okay, this is trim. But if he starts daydreaming and makes a mistake and cuts not on the line, that's then reject. Let's just throw the whole thing in the bin. And you want to avoid this when you're making parts at volume, because you're not throwing one jacket in the bin, you're throwing 200,000 jackets in the bin. Yeah, so it really adds up. So that's your materials. Then you've got your production costs, your overheads. You need people in the factory. You have to consume energy to make your parts. You need a molding tool. You've got your equipment that you have to purchase, your capex, and that adds up to give your what we call a factory cost. And then onto this, you can add your SARD, your sales, administration, and R&D costs. Because if you spent 5 years developing the product in your startup, well, you've got to pay for that somewhere. And you can put that on as a SARD, or you can add that separately in a business model, for example. So that gives you the total operating costs, but you want to make some money somewhere along the line in an equitable way, for sure. And you want to have a gross margin, and you have to pay some corporation tax. So you need to think about not just the cost, but the price. And this is the subject of a later lecture on some kind of business economics. Some different approaches to cost modeling. If it's an established process like steel stamping, you'd use activity-based cost modeling because you'd use historical data. You can go around a plant with a stopwatch, you can clock the process, you know what you paid for the equipment, you know what it costs to pay your staff, you know everything. You can go around and you can clock it, okay? So that's not so useful if it's a new process, because you don't know all these things. You don't know the cycle time of your composite molding process. You can simulate it, you can work it out, but you don't actually know. How much does the machine cost? Well, how big does it need to be? We need to work it out. So then you go to a technical cost modeling approach, which is very suitable for new processes rather than historical processes. And you can use technical cost modeling to compare with activity-based cost modeling. So you can model a steel seat with an activity-based costing approach, and you can model composite one with a technical cost modeling approach. Okay, you can do that. These are some of the things that you can get out of a cost model. Well, the first thing is a number. You can get, it costs 35 euros. Beyond that, you can get a lot more information. This is a Mercedes E-Class body and white structure, and we've modeled different components in this. And later on in the lecture, we're going to look at this rear structural bulkhead, which is part of the body and white. And we did this cost modeling case study for Mercedes. First thing you can look at is the cost against manufacturing volume, because if you're making 2,000 McLarens, or are you making 200,000 Mercedes, or 1 million Ford F-150s? It's different volume, and the process you choose can change. It's a different decision. So one answer can be right at low volume, and a different answer can be right at high volume. You can then do sensitivity studies. You could do a 10, 50, 90 proper kind of sensitivity study looking into the future, which technological innovations can actually enable your process. So later on, we'll see how the cure time of the composites is important. And actually it's changed in the last 15 years. It's got much faster than we even predicted. This is very good for doing what-if analysis. So if you present a cost case study to a customer, they'll say, yeah, but if we do this, what would happen? And then, oh, yeah, we can put that in the model and we can see, we can talk about it. It's a dialogue. You can do a Monte Carlo simulation. You can use design of experiment tools to make surface plots. And all these things you can build from the kind of model that we've put on Doodle for you. It is a very simple model. It doesn't do everything by any means, but these are the kind of output that you can get. You can start to segment down your costs and see where the cost drivers are. And you'd be surprised how many companies don't do this really very well. Some do it very well. It's important to know that. So imagine we're making this composite part, which is a mix of a composite sheet and some over molding, injection molding granules. I hope you all know what injection molding is. Okay, so this is like a plan view of a factory, and it's very helpful to draw, before you do your cost model, draw your process flow. What is it that we're trying to model? This is like a plan view of a factory. The reason is, in the technical cost modeling approach, you need to get an estimate for each of these items. So what does your stamping press cost? Well, you can work out what size it is. You can call Dippenbacher, who make presses, and you can ask them for a quotation, and they'll give one to you. Okay, ABB for a robot, and you can start to estimate the cost for making this part. And you can do that more easily for one machine than for a whole factory. Who do you call up? What does a factory cost to make a seat? No one knows. You have to work it out. Okay? So as you go around the process flow, you're consuming resources. You're consuming materials in the process flow, energy. You're consuming operator time. There's CapEx. There's the energy to run the equipment. You need to pay for a factory. So you're accumulating costs as you go through a process flow. You might need to buy some subcontracted parts from another company and assemble them on. You may need to pack and ship parts to a final assembly plant. This is a production line at Mercedes, and we included this in the model, the cost to manipulate the part and put it into the embody in white. So you have an apples to apples comparison between the incumbent, in this case magnesium, and the real parts we're looking at here in composites. This is critical to draw your process flow. If you don't do this, you tend to get completely lost. So the approach of a cost model is to follow the progression of a process flow for your product. You might need to model different process flows to compare different strategies. So you divide the process into the contributing process steps, and each operation contributes to the cost as you consume resources. So you need to basically add up the accumulation of costs as you go through that process flow. And that reduces a complex cost estimation problem of that steel stamping plant, what does it cost, into some more simple estimating problems. As an engineer, you can call up a company and say, hey, ABB, we need a robot that's got a reach of 1.5 meters. Can you give us a quotation? That's a simple estimating problem, okay? The kind of elements we talk about are an overall plant, which could be multiple manufacturing lines. So you have to assemble several components together. Then you have your line, which is like here, a line to make one piece. Inside the line, we have a cell. And we like to break it down into cells because this machine might have a different cycle time to this machine, okay? So you can't model them with the same cycle time, or maybe you can, but it's nice to have them separated out, and then you can see which cell is contributing to your overall cost. One of these cells might be novel, and you need to model it differently to the others, okay? You might say, hey, let's subcontract cell 2 to somebody else. Let's not do it ourselves, okay? So you break it down into cells, and then machines, and these are the easiest things to get the information for. Another way of looking at this could be a kind of flow diagram like this, where what you have to do is to make an assumption for your plant with some initial data, and we'll come back and look at that in a minute, which describes the cost structure for your plant. You need to have them at different materials, how much you need to buy in for your parts, that's very important. What does it cost per kilo? Okay. You could look at different material suppliers, and then for your equipment, start to look down at the power it uses, how much it costs, how big it is. If you're buying a small press or a big press, you need different space in the factory. Tooling, this is always part specific. So if I'm buying a molding tool to make a seat, I can't use the same molding tool to make a car door. Okay, that's always has to be amortized just across the seats that you're making. Whereas the machine, we'll see later, that can be treated differently. You need your labor, how many shifts you're running in the factory. So all these things go into your cost model. And it's just important to stress the importance of data quality. When you're making a cost model, see it as a scientific exercise, be rigorous. You might need to use some experiments or some simulation tools that are very popular. We can use mold flow to work out the tonnage of the press to inject the parts. So you can include the physics. You can do some experiments in the lab. You can pay Veronique to do some kinetics of the epoxy, okay, to work out the cycle time. And people do this, okay? So don't just guess. If you're guessing, you need to highlight this and try and do some sensitivity around the number, okay? But you need to reduce uncertainty in your input data. Otherwise, it's garbage in, garbage out, and you're not really helping. So another way of you can build up data with experience. People who are skilled in the arts will know the numbers from doing it 3 times before. So if you go to an injection molding company, which is always bidding for Mercedes to make this seat, they know what the machines cost because they have them in their factory. Then it's starting to become an historical process. What we're going to show next is an example of experience-based regression models. So this is an injection molding machine, which is used to inject plastic. So it injects the back material here onto the composite, back injection. Injection molding is a very well-known process in the industry. So you can easily get data to correlate, for example, your injection molding machine tonnage to investment, okay? And you can even make an expert tool to model this. So here it's simple to model these processes because you have good data, but for other processes, you won't have such good data. Here's another example of an extreme case of a factory. You all know what Lego is. Well, they have 672 injection molding machines, and they're popping out these bricks by the billions. But they have to work out what they cost so they can make their gross margin on each Lego brick. They might want to make 40% gross margin. That's what I heard. And they have to set up their factory. And this is in a case of extreme optimization. But to go into your factory, you need to work out how many years you're going to make this seat for, because that's how long you have to amortize the molding for. Your number of days you're actually making parts. Factories don't make parts every day of the year, because you have to stop to service the machines. Okay, they don't run non-stop. How many hours per shift? Sometimes you can seamlessly start and stop shifts. Sometimes you need to do some maintenance, clean the mold. It depends on the process. You've got to pay your people, and that changes depending upon your production location. Is it in Europe, North America, Asia, China? You have to pay your energy. Your plant costs money to run. You have to include this. Surface correction factor is because the injection molding machine doesn't just sit on a piece of land. You have land around it, so you have to multiply this up. This is very densely packed. Other factories are much more spacious. You've got to pay back the bank some interest on the money you've borrowed to pay for your equipment. And then you can say, well, how long does your machine last for before you have to buy a new one, if they don't last forever? And again, that's the time period you have to make money on the investment you've made on that machine. Okay, so let's say you're making this seat structure, and there are different ways to scale up in volume. The first thing we can do, this is a production line where you're taking a composite sheet, heating it, molding it, and trimming it. The first thing you can do is say, well, I have one shift of 8 hours. People come in, they run the machines, you pay them, you make parts. That doesn't make enough volume. You want to make more seats than that. You can bring in a second shift of people to work in the night. And this is standard practice in automotive tier 1 suppliers. You can even have 3 shifts. One of the issues with composites is their cycle times are longer than metal. The steel video, they're popping out parts every couple of seconds, non-stop, boom, 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 boom. Okay, it hypnotizes you. Composites, it takes a minute to make this seat. So you might need to buy a second machine, which means more CapEx. You have to invest in a second press, okay? And the cost model can include this. So the manufacturing line you have at low volume isn't necessarily the same line you have at high volume. So when you're making a cost volume curve, the first part of the curve may be with one press. The second part of the curve, you redesign your plants, and then you have two presses. Okay, so be careful how you extrapolate with volume on the capex that you have. We talked about the tailor earlier on, making the jacket, passing off trim. Okay, this is something you really want to avoid, especially when you have a long process flow, because these costs accumulate in the process flow. So if every machine has 2% scrap, and you have 10 machines, you're buying a lot more material than is in your final product. You're having to pay for this waste, it goes in the bin. And if this is composite and it's carbon fiber, you know what this costs for your exoskeleton, yeah? Do you really want to throw 30% in the bin? People do, okay? And innovation has the role of addressing these things. So in a cost model, you can study this. Going back to a manufacturing plant, simplest case is you have processes that are in a linear flow, one after the other. In a more interesting or more advanced case, you'll have some converging flow. These could be two different lines making two parts that are assembled. This is the tool you've been given to model a linear flow. You'd need to do some tuning. We have more advanced models that can handle converging and diverging type flows. Something else you can do, I talked about the role of simulation. Okay, again, this worked yesterday. I don't know why it's not working this morning, but here it is, it's now working. Yeah. You can actually do a simulation in CAD of your process, okay, to work out the actual time it takes to do the operation. Without buying the machines, this uses the embedded hardware controller of the robot to perform a simulation. And then you can say, well, the cycle time is 10 seconds to get the part in the mold. And then when the person you're talking to says, well, how did you calculate the cycle time? Did you guess? No, we simulated it. And this adds authority to your business case if you can use virtual tools to simulate the process. And this is the cell that was used to make the seat before the cell was invested in Sweden. Okay, this is what we had to do to convince the stakeholders.
How long does it take to make a model like this?
If you know what you're doing, probably a couple of days.
You need them exact geometry of the machine.
Yeah, well, this is a rough geometry of an injection molding machine. This is the exact CAD of the robots. ABB sells simulation tools with their robots to do this, or you can buy generic ones, and that's the exact CAD of this part. Okay. So by using virtual engineering, you can reduce uncertainty in your costing. So we can start to look at how can we segregate cost elements. And depending on which hat you're wearing, if you're Thomas, you'll be interested in CapEx and OpEx, your capital expenditures and your operating expenditures. If you're an accountant, that's how you think, okay? So your CapEx are the things you need to buy. We typically think of equipment, but you have to buy the plant as well, buildings, to run your equipment. And then you've got your operating expenses, salaries, your research and development, administrative, these kinds of costs. And what's interesting is you can actually cheat and lease equipment to move it from CapEx to OpEx. You don't have to buy this injection machine. You can lease it, okay? We did that at DuPont. So this is where basically you have a cost model and you can take out of it things that you want. So if you're just interested in costs, you wouldn't necessarily do this. If you want to link it with an NPV or return on investment model, you would simply drag out of the cost model in these two categories to help with your predictions. The other way of looking at this is looking at fixed costs and variable costs. Fixed costs are typically these one-time capital expenditures. Variable costs are things like materials, which don't vary with your manufacturing volume. But can anyone think of an exception where these variable costs could actually change with volume? Okay, if you're making 3 parts of these back systems, or you're making 200,000, material cost wouldn't be the same because you'd negotiate on that. Okay, so everything is negotiable in this cost model, and you can move things around. You can put if statements in. So up to 50,000 per year, we pay X, and then we pay less. So you can build this into the model. Okay, so it's very flexible. Here are, okay, now we can look at some depreciation. You have to depreciate your assets over its lifetime. We use linear depreciation in these models. There are other ways of doing it, but this is very commonly used. In an extreme case, if you say, well, we're just going to buy this cell only to make this seat, and we're going to decommission it, you have to amortize your plant costs over only 3 years. So if you have a new technology and you don't have another project to run on the line, you have to amortize it only over the time you're making parts for. Because afterwards, it's not earning money anymore. So we have to depreciate the assets. Tooling is always dedicated to parts because it's a shape-specific tool, unless the tool is flexible in some way, of course. Now, the cost model, which Professor Michaud was going to show later, can give this kind of output, okay? And you can start to see some fixed and variable costs in here. So your material value here is constant, okay? Whereas your machines are being depreciated, assuming they're dedicated, and so is your tooling. So they're varying with volume. Your energy is constant with volume. Your labor is assumed constant with volume. If you want to change that in the model, put in an if statement. Maybe labor gets cheaper with scale. Maybe a high volume, you change production location. You can simulate this, yeah? And you can see how the contributing cost elements also vary. Material here is constant with volume. You can see the depreciation is not constant with volume, and nor is the tooling cost. So it helps you to understand your process using these kinds of tools. Okay, we've been talking about plants. There's 2 ways to amortize plant costs. The first is to say we can only make seats on our production line. So we have to pay for all those molding machines just to make seats. And we say that the equipment is dedicated to one product. So we have to amortize it only over the volume this is made for and the number of years that it's made for. This is typical for new technology because you don't have another customer. Okay? Another way is to look at a utilization-based approach, maybe for an established process, and you say, well, you know, our machine can make 200,000 per year, so we're going to make seats for Volvo and bulkheads for Mercedes because they only want 50,000 and they want 80. So we've got enough capacity in our line to just change the tool and keep the line the same and mold 2 different parts. Which is the cheapest? Okay, well, this one is cheaper because you're sharing the capital expenditure between 2 different products. Okay? So you want to avoid dedicated plants. This compares a utilized and dedicated plant for magnesium die casting. And just to be aware, the scale is not the same. This is how you cheat with data. Okay, so the dedicated plant at low volume is a lot more expensive than the utilization-based one. Here you're assuming that if at 20,000 per year, all the other capacity is paid off by a different product or client. Okay, if you can assume that, it's a really nice case if the cost really falls. If you can't assume that, the cost goes up. And in the tool that Veronique will show you, you have a tab where you can switch between utilization-based and dedicated. So typically, as I was saying, established technology is a utilization-based approach. In the automotive industry, they have open book accounting, where the OEM and the tier 1 will sit down and look at the cost together. And they typically assume that remaining capacity is your problem. Okay. Novel technology, you tend to need to look at a dedicated case, which can really penalize a new technology against an established one, because you have to pay for this equipment. Okay. So just going on to a few more topics in this deep dive, we talked about cells being dedicated or utilization based. And that's why we break it up into cells so we can pull them out and change the assumptions by cell. Okay. In a process flow, you're always going to have a bottleneck, and we can adjust the cycle time of the cells to match the slowest one accurately. Or you could say, well, this one's independent because we're able to, this one is twice as fast as this one, so we can use it for something else. So in more advanced models, you can start to play with the way the cells work together in a process flow. Going to have a quick drink of water, tea. One of the things we see when we model. Sorry.
Sorry, I had a question about the dedicated line versus non-dedicated line graphs. On the non-dedicated line, the depreciation of the machine was not decreasing, or
Yeah, that's because you're assuming that the machine is fully used, so you're paying for a cost per minute. Okay, so you're assuming that all the other time that Thomas is paying for that with his projects, and Veronique is paying for the low volumes, and we assume that somebody else is going to pay for the rest, so you're paying for a cost per minute. If it's dedicated, Veronique has to pay for it all. She can't share it with anybody. Okay, so that's the difference. It's a good question. One of the things we see when we model processes is the importance of the part mass. That's your bill of materials, your materials going in. Lots of things that you make, you have to buy raw materials to make your product. And it can be really important, and it's very sensitive. So one of the things I would really encourage you to do is to use virtual prototyping, simulation, CAE, to simulate your process, look at your part performance, because if you get your mass wrong, your cost is wrong. So here's an example from the seat, okay, where we did this case study. We looked at the load case of the seat. We have to meet certain requirements for crash performance in the car. We do some CAE, and we prove we can meet the load case. Well, that gives out your part mass. And part of your value proposition is, hey, we can save nearly 40% weight versus steel. Well, how did you get there? Did you guess? No, we simulated it, and we spent a long time and lots of money on testing materials and developing models, okay? So we have quite high confidence in our weight saving. And what's interesting is when you design your plant and you look at the cost, this is the cost of the frame, and this is the other parts that assemble onto it. So take this frame cost and look at the breakdown of that, and you see the dominance of material cost. So if your mass estimate is wrong, your weight saving estimate is wrong, and so is your cost estimate. So it's really important for the most sensitive parameters to spend quite a lot of time getting them right. And that adds credibility to what you're trying to do. Go on.
How accurate are these finite element simulations of the composites when you compare to actual stress tests?
Yeah, I mean, we can get over 80% accuracy. The stiffness is very accurate. The strength is pretty good. The crash, it takes a lot of work. So the stiffness, 1 PhD, crash, you need 3 or 4 to do the work, and it takes a lot more time. What we do is we validate them on a coupon and then a generic part to prove that the CAE is working. So you make a part and you physically test it to prove it correlates, and then you can take an unknown case and say it's going to be close because we've proved it on generic parts. Okay.
When it comes to the CO2 consumption of cars using the seats, how much does it change?
We're going to come to that after the break. Yeah, very good question. So this is just looking at cost by itself in a vacuum. Okay, and later on we'll come back and look at that. And then you need to look at your business financials as well on top of this. You can go one step further and do a process flow simulation where you run your process multiple cycles and you have failure probabilities, which you can use based on real data. So if your part gets stuck in the molding tool, you've got to prize it out. That's quite quick. If the hydraulic pump on the press goes down,
you may have a 2-month wait for the pump to arrive from China during COVID, okay? And this is what affects the real reliability of a plant. So you can do that to make your model more refined at a later stage. So the closer you get to spend money, the more detail you put into it. Okay, looking at time. I'm going to skip through this really fast because we had a separate talk at the beginning. But when you're in industry, you'll have an idea and you want to try and create value and get to the customer. One of the things you need to do along the way is to understand the cost and the CapEx involved. Okay, and this is a tool to help you, and you'll be assessed against other projects going through this funnel to look at the NPV of your idea against somebody else's. And the better you can show your cost case and the more accurate it's deemed to be, it increases the chance you're going to get funded, really. And this is particularly true when you're looking at a new product in a new market or the same market. You need to really understand the cost. In existing markets where you have the same product, you've got the historical data, but if you're going into the risky quadrants over here, you need to understand your cost, and your stakeholders will expect you to understand this. And part of the cost is your CapEx, and that's the investment you're asking for from the bank. Hey, I have a startup, I want to make self-healing composites. I need $2 million for a pre-threading line. Whoa, well, what's your cost case? You know, they want to know if someone buys this pre-preg, does it have an advantage? Okay, so cost becomes investment and it becomes risk.
I can say something there from my own experience, because then you think, okay, if I want to make my startup, I don't have the money, so I cannot start. And so then you're like, well, then there's no way to do it. And the way to do it, it's a high risk, but lower cost, is to subcontract some of your operations. So you say, okay, I don't have 2 million, I cannot buy a pre-fragging line. And in any case, if I buy one for producing, 100 square meters when it can produce kilometers, it's stupid, because then, it's really too expensive and nobody will give you money to buy this unless they know that you're viable. So the thing is to subcontract to some guy who has a line, and it's a utility base. And then you say, okay, you pay more, but you subcontract, you have to make a good partnership. And then it's only after, and I know some startups that are not startups anymore, after 10 years or so, they start to think about buying their own pre-fragging line and becoming independent. But it's a very risky operation, because if the guys you are contracting from say, oh, but Mercedes is coming with 1,000, Boeing is coming with 1,000 things, so you are behind because you're the little guy, we're not interested in you, then you're in really bad situation. So it's a very risky situation, but that's the only one as a startup that you can do to kickstart. So
yeah. So okay, another couple of minutes and we'll have a break. One thing Mercedes had us do was to plot all the processes against the kind of standard S-curve, because you're being compared against an established process, steel stamping, magnesium die casting, and you're down here, you've got this great idea right in the birth stage, very high risk, and they want to have this established cost picture, but you're here. So just be mindful of that. One other thing cost modeling is really useful for is developing a value proposition for your product, which is a compelling promise and set of desired attributes that your product has, that differentiates it from an in-kind or non-in-kind incumbent, okay? And its total cost is attractive. And this is specific to an application. Some people like to say the value proposition of a composite is this. No, the value proposition of a composite seat is this. And it's always specific to a customer and to an application. And it needs to be quantified, okay? Money's involved, you're exchanging something for money. So you need to try and quantify it. So cost modeling is really important for this. Just wanted to stress that. We're running out of time. Quick few comments on comparing a idea with an incumbent, which is here is steel. And an OEM, a car company, might just give you one number for that seat and say, hey, please come up with a solution that's cheaper. But what is that number? Always ask what that number is, because it might be cost, it might be price. they buy it from a tier 1 supplier, so they're paying their margin. Okay, you have to dig. You might need to get some consultants involved. So it's really important when you're given a target number, always to ask questions. Does it include tooling costs? Okay, ask. Here is just what Veronique was saying about strategy to minimize capex applying to making laminates. So you start off and you say, well, this machine is 20 million euros, double belt press. Our customers haven't adopted. We don't want to invest, it's too risky. But how can we give them samples? Well, to start off with, you can subcontract. You find another company that's got this line and you buy some of their spare capacity. You pay a bit more, for sure, but your risk is really low. Then you can set up a tolling operation with a specific contract using your own know-how. Then you can buy a small machine as the market confidence goes up and eventually invest in a bigger machine. And depending on how conservative you are with risk will affect how you climb that cliff, depending on your access to funds to buy the equipment. You climb this cliff in a different way, but to try and climb the cliff in one step tends to get no from the people who have the money. So be careful. Look for solutions to dodge that, like Veronique was saying. So we have a break, and afterwards we're going to look at some of the sustainability links to cost modeling. So we'll take 10 minutes and then we'll carry on. Okay? So you've probably all been watching COP26 and all the talks, and investment is a key thing in the future for addressing climate change. Money is very important, and all these technologies they're talking about, wind and solar and other things, they all need to be understood from a cost perspective. But what can we do beyond cost? But what we did in the lab about 15 years ago now is we coupled together a cost model, a life cycle analysis model, and a life cycle costing tool for a case study based upon this rear bulkhead, where the incumbent is high pressure die cast magnesium. And we looked at some different structural materials, steel, which is heavier. That wasn't the OEM's interest, but that was added in for reference, and some different composite solutions. Now, I'm going to highlight a couple of things in this study which in hindsight could have been done better. Hindsight's a wonderful thing. In the previous study, when I showed you the cost, we had some weights that were 1.2 kilos. In this study, it was assumed it was 1.8 kilos for the composite. And this turns out to be a real issue. So keep that in your mind as we go forward. Okay. Which material would you say is missing from that list for automotive industry? Making a car part. Which material is missing? It's aluminum, exactly. That is the de facto lightweighting material of choice for automotive, is aluminium. Okay, so you always have to, don't get lost in the micro. You've got to look at your competitors and the macroeconomic picture. Don't just get lost, because that's a critical thing that's missing in this study. Okay, bill of materials. You need to understand your material prices. This can be pretty hard to get hold of because they're people's bread and butter. But you can see the big difference between carbon fiber-based materials and glass fiber-based materials. So we needed to get good quality data, which Mercedes gave us from their suppliers. So we had good data. But if your mass is critical of your parts, so is your material cost. Okay. Now your mass you can calculate on simulation, but material costs, you might need to do some what-if analysis, okay? Look at historical data, say, what if the price comes down by 10%? How sensitive is it? Probably important, but then you can discuss it when you present it to your client. So this is the base process. Mercedes gave us a point number for this component. So we had to model the cost against volume behavior using a tool. And we calibrated the tool with Mercedes, so it gave the same answers as their tool for this part. So we knew we were comparing apples and apples. That's the first thing we did. And when we looked at the magnesium price, because it had a historical variation, it was quite large. Okay. We then said, well, how can we make this in carbon epoxy? And this is an interesting example because 15 years ago, the cure time for an epoxy was around 10 minutes pre-preg, whereas now it's come down to 1 minute 30 seconds for the pre-preg that's being used on the BMW 7 series. So you can then throw away half of this plant diagram because the kinetics of the material mean you don't need all this capex to mold all these parts. Okay, so that should go into your sensitivity study, reaction kinetics. Okay, your engineers, your scientists at base, always look at what's driving the assumption and look at it in detail. So that had lots of trim, and that's what you were doing. In the last example, we were taking a roll of material here, like the tailor, and we're cutting it out and we're throwing 30% in the bin. Now, hopefully you're going to recycle that, but this is carbon fiber. Come on, guys, what can we do? Well, you can invest in a robot that can place this material to a near net shape. So you get rid of the waste. Further, you can align the fibers rather than having a random material as is assumed in the life cycle study, okay? So we then said, well, how does this nice process compare with the pre-preg? So the pre-preg is in blue, and these are the different shifts. We're buying a new tool with volume. You'll see these things come up just in a second. And we have curves in green, which is the utilization-based case. It means you're buying this robotic cell and for Veronique, and you're assuming there's a Thomas who wants to use it too. Is there? If there's not, then you need to look at the orange curve. If there's no Thomas, then your costs go up, and Veronique has to pay for all of this, okay? So critical with novel technology, how are you going to amortize this novel plant that you've developed, which is really wonderful. The next thing we can do with a sensitivity study is to say, well, here's your pre-preg, okay? This is cost with changing volumes. If we can decrease the cure time, well, that was what we dared say to Mercedes 15 years ago. Turns out we were completely wrong, and Hexcel have got down to 2 minutes or 1.5 minutes with their latest pre-pregs. So that would change your equipment cost if it's utilization based, because you're spending much less time making it and there's more spare capacity, okay? And if you can then say, well, with this robotic process here, we get rid of the trim, well, your equipment cost may or may not go up. If it's utilized, no. If it's dedicated, yes. So if you combine some automation and some chemistry, you can chop down the part cost by a significant degree, okay? So Mercedes may say, well, this pre-preg is far too expensive to use in a car. They're right. But maybe there are some alternatives which we can model and convince them to invest, which bring the cost down. So this is talking about the cost of the component still. And what you can do with the sensitivity study is to say, here's your magnesium, carbon fiber. Well, these are the established technologies. This is a kind of bubble of models of several different plant diagrams and material assumptions. You can then say, well, if we can start to have some emerging technology, how far does it come down? And then emerging technology with some reduced material costs. As volumes go up, material costs should come down. And you can see where your future kind of probabilities lie for the process. Where could it go? You can do the same thing mixing glass and carbon, because glass fiber is cheaper. And then, but it's heavier. This is your part mass. This is your magnesium. And automotive want to save weight to reduce CO2. Carbon saves the most weight, but it's more expensive. Glass, it turns out, is basically flat over magnesium. There's no weight saving incentive, little part cost incentive. So why would they change? What's the value proposition for a glass-based composite compared to magnesium? It's much more limited. Carbon has a stronger value proposition if you're prepared to pay the money to have it. So that's what you can do with a cost model. And these are, again, all individual runs of a cost model, and you can start to relate your cost increase versus magnesium against your weight saving versus magnesium. So we need to be saving weight. If it's cheaper, it's perfect, but that's quite hard. We don't want to be heavier. It's not what we want. We don't want to be heavier and more expensive. We want to be here, but within an acceptable euro per kilo weight saved. So you can start to say, where is the technology going and how suitable is it? So that's all done using cost models like you're going to see later on. This is the kind of thing you can do with it. So that's cost, but what about the life cycle impact of the materials that you're looking at? So we go from the raw material extraction, transforming this into a semi-finished product, making the part, then you have to assemble the vehicle, and that's your factory gate. So it leaves Sindelfingen in Stuttgart, your nice new Mercedes, which none of us have. You then go to the use phase where you drive it around, and then after 10 years, it goes to Africa or it's put into a shredder. Okay, so we need to look at the life cycle impact, and you can do this following a linear economic model, or increasingly we need to look at following a circular economic model, because a linear model is just full of waste. It's full of opportunities to improve. So this is what you need to do a life cycle analysis, which we're going to show you in just a moment. And there's a separate lecture on this by Jerome Pillet, if I understand correctly. So your raw material extraction. So you need your oil, which you can crack to make adipic acid, and you can make your nylons. These are for composites, for steel, for magnesium and aluminium. You've got your transformation stages. And what's interesting is the data you need for a cost model is quite similar to what you need for a life cycle analysis model. We've been talking about component manufacture, but a chemical company will run cost models on the earlier stages as well. So it's very similar data that you need in many ways. And the case study we're showing you really follows a linear economic model. It hasn't included these aspects of the circular economy, which we need to focus on more in the future. Okay, so it's not enough to lightweight a car following the linear economic model. We need to lightweight it following a circular economic model in the future. So that's what we start to do.
Ask you, so would that, in your opinion, increase the cost or decrease the cost?
It's a good question. It depends on also on how you cost your raw materials. Do you cost them based upon what you pay, or on the environmental impacts that they occur during their manufacture? Okay, if you did the latter, it would be a different answer. What I would say is, how will it change cost? Well, the vehicle, a Tesla, is very different from a Mercedes E-Class from 10 years ago. This is mainly steel. A Tesla is aluminium. Tesla's got a massive battery pack for sure, but Volkswagen are now saying we'd rather lease the car, and at the end of the vehicle life, we own the lithium in the battery. Okay, so it's not just about the cost; it's about the business model as well. Okay, and if you make the vehicle last longer, you can have a kind of lower platform into the vehicle, which does last longer and can be reused in some way. Okay, so trouble is today, what do you do with the carbon fiber waste? Everyone's seen the BMW i3, which has carbon fiber in. Well, some of that carbon from the manufacturing stage is turned into a random mass and reused in the vehicle. But at the end of life, what happens? It's not talked about very much. Okay, so we need to start to close loops in the process. And I think it can increase efficiencies, but it may also push up some costs. And some people say it will reduce margins slightly. And we have to increase the amount of retained income for R&D. So the shareholder might see a small cut, but that's a completely different topic. So this was a coupling of a cost model with a life cycle model. So you have to have your production plant, and this is the relates to the manufacture of the components. So you have your materials coming in and the transport in the life cycle study. Here you're making the components, and you're buying in materials which have associated ingredients, and those ingredients incur a life cycle burden on their production, okay, depending on the mass. And the functional unit is not per kilo, it's per part, okay? So if you save weight with composites, it's not per kilo, you're using less of it. It's really important that it's on a functional unit. So we modeled this for all those different magnesium and composite scenarios, combining output from a cost model. So here we can work out the power we need because we've modeled the plant. We know how much power the cell uses. We know the people that are involved. We know the materials that are involved. And then you can use another software, Sima Pro, which has the life cycle burdens for human health, ecosystem quality, climate change, and resources for both the raw materials, but also the steel in the press. You have to buy a press, that's made of steel. The steel has a life cycle burden, and all that goes into this model. So this is what we get. These are the examples. We've got steel, we're missing aluminium, whoops, magnesium. This is carbon fiber parts, glass fiber parts, in thermoset, in thermoplastic, and in thermoset. And they've got different weights. So the functional unit is per part. The steel part is heavier, okay? So this is the primary energy involved in producing the component. And it also has the use phase in, okay, here. Now what you see is that the use phase dominates. And that's pretty much always the conclusion with transport. It doesn't mean that you can do what you like here with the raw materials and manufacture, or that you can forget end of life, okay? So the use phase is important, but you can't just say, forget everything else. Here's human health, climate change, and the ecosystem. And what you see is that as you save weight, you're reducing the overall climate change impact, look at CO2, apart from for magnesium. It's like, what on earth is going on with magnesium? And what happened is there was a critical assumption around magnesium, which was assumed to be made in China, okay? And they used the so-called pigeon process, and magnesium is very volatile. So they use FF6 to suppress the oxidation, and SF6 has a global warming potential relative to CO2 of 24,000. But the life cycle analysis model assumed that all of the FF6 was lost. Not true, doesn't happen. So when you run a model and you see an unexpected result, you need to start digging and work and checking and questioning data. Don't just take what someone tells you as the truth. It might well be based upon an assumption which is not right. So then you could recalculate this and assume the FF6 10% was lost. What would then happen to your diagram? Okay. The other thing that I would point out is the mass here of the carbon fiber part. They assumed a random fiber carbon, so the fibers are all random. Okay. Carbon is best when it's aligned, and then the mass drops to 1.2, and that will change the results. Okay. So this is then your life cycle costs, including raw materials, manufacture, use, and end of life, which doesn't really appear. Something's going on with that as well. We're not really including the true cost of end of life. So the carbon, the raw materials are expensive for sure. And what we've seen in the industry is a drop in the cost of carbon fiber and the way it's made. So BMW, when they made the i3, they use wind power for their carbon fiber plants, not fossil fuels. Okay, they use bigger carbon fiber bundles, which are cheaper. Okay, so things change with time. Always check and ask questions, ask why. But you can see the overall life cycle cost of steel is the highest. And if you imagine when you refill your car with petrol, each time you do it, you're pouring in 80 liters. How many times do you fill up a car in a year? Times 10 years. How big is the tank of gasoline that you've burned in your car? It's a huge amount of fossil fuel. So that's and that's expensive. So that's going to govern your life cycle cost. So saving weight is really important if we can do it in a sustainable and circular way. And the OEM is interested in these aspects here, in the raw materials and the manufacture, because the OEM, Mercedes, is buying the raw materials and it's buying the plants. Then it leaves the factory gates and you are paying for the petrol, not Mercedes, okay? So they'll have an innovation headroom allowance to spend a bit more on the car, assuming you want to pay for it, because there's some savings down the road, okay? And that's going to change with electric vehicles. It's not going to be the same way of thinking. There's going to be, range becomes really important. So if you can make the vehicle lighter and your range can go up, people will start to pay more for it. Today, carbon fiber is used for performance in vehicles, okay, not for economy. Mercedes used it in their 7 Series and their i3. Yes, that is also economy, but predominantly it's used in supercars, okay? So you can then start to do a sort of break-even analysis. It's not really a financial break-even analysis, but cost against kilometers. So that's total cost of raw materials, manufacture, and life cycle costs, comparing different materials. Your baseline here is steel, this line here. Okay, so you're spending lots of money as you use it, as you drive more and more kilometers. You can spend a bit more money, and with glass composites, actually you can break even at quite a low distance. The carbon fiber doesn't look very good because of its weight, because of the reactivity of the polymer, and because the fibers they've assumed they've got cheaper time. So if you redid this today, that would be much more attractive than it was 15 years ago. So with these modeling tools, you can do projections of technology to show where things are going to go to. This shows CO2 against life cycle cost, and you want to be low. Okay, the lowest is the glass material. Magnesium is high because of this pigeon process. Steel is the worst, and that's why the industry is moving to aluminium. So aluminium, particularly when it's secondary aluminium, is very attractive. So coupled cost and life cycle analysis, it helps you to really look in more detail at a material choice. What it's not doing is looking at the business case, the NPV and the return on investment. Okay? So it doesn't go all the way, but you can couple these models into those and then look at the business case as well, which you need to do. You can't stop here. Okay? But for the future, we need to really watch the data. You know, when we were in DuPont, we had access to the real data for the polymer, and we've got the real data for the glass from the glass company. And it's not always the same that is in the life cycle tools. Okay, so you need to really make sure your data is rigorous, and it's best done in collaboration with other people, and you get the best result. So we need to design out waste and pollution in our processes, getting rid of the trim, for example, trying to keep products in use, and we need to regenerate natural systems. We can't just look at cost by itself. And people like to talk about the triple bottom line. Traditionally, we looked at profit, we looked at cost, we looked at return on investment. We've got to look at people and the planet, okay? And just one really small thing to point out is that life cycle analysis doesn't address all of the UN Sustainable Development Goals. Small print. It's a brilliant tool. We need to use it more and more. So I've gone really quickly through the last bit to give time to look at the costing tool. So I think that's